Welcome to your Algebra 2 Lesson 1.6. Today we'll be talking about solving linear inequalities. So that's your objective today, is to be able to solve linear inequalities. Okay, so a linear inequality in one variable can be written in one of the following forms where a and b are real numbers and a is not equal to 0. Ax plus b is less than 0. Ax plus b is greater than 0, ax plus b is less than or equal to 0, and then finally ax plus b is greater than or equal to 0. A solution of an inequality in one variable is a value that, when substituted for the variable, results in a true statement. The graph of an inequality in one variable consists of all points on a number line that represents solutions. Okay, so let's go on to example 1. And in example 1, we're just going to graph simple inequalities. So our first task is to graph x less than 2. The solutions are all real numbers less than 2. An open dot is used in a graph to indicate that 2 is not a solution. Our solution begins at 2 but does not include 2. So you have an open circle at 2 and then you color in on your number line in the direction where all the values are less than 2. So that would be to the left. So you start with an open circle at 2 and go to the left. Now for part B, we're going to graph x greater than or equal to -1. So the solutions are all real numbers greater than or equal to -1. So a solid dot is used in the graph to indicate that -1 is a solution. So anytime you have or equal to, you use a solid dot. Okay, so we draw in the solid dot at -1, and then we color in the side of the number line in the direction of all values that are greater than or equal to -1, so to the right, because values like 0, 1, 2, 3, those are all greater than -1. Okay, for example 2, we're going to graph compound inequalities. A compound inequality consists of two simple inequalities joined by and or. For and statements, everything must be true altogether. For or statements, one statement or the other must be true. So we're going to graph -1 less than x less than 2. So the solutions are all real numbers that are greater than -1 and less than 2. So both things have to be true. The x has to be greater than -1. It also has to be less than 2. And it's nice the way it's written. See how the x is kind of written between -1 and 2? So you're going to color in the part of the number line that's between -1 and 2. Because they're both strictly less than, we use open circles for both endpoints. So we have an open endpoint at -1, an open endpoint at 2, and we indicate that all the values in between are solutions to that compound statement. Now we're going to graph an or statement. We're going to graph x is less than or equal to -2 or x is greater than 1. The solutions are all real numbers that are less than or equal to -2, because see the little line underneath the less than sign, that, remember, that means or equal to, or greater than 1. So we include everything that makes one or the other statement true. So the little left arrow there that has a solid circle at -2 and extends to the left on and on forever there is indicated by the arrow that's colored in. Those are all the values that satisfy the statement x less than or equal to -2. On the right side, we have an open circle at 1, and then we have the section of the number line colored in that's to the right of 1, because all those values satisfy x greater than 1. So for or, you include both parts, whatever makes the first part true as well as whatever makes the second part true. Okay, I'm going to go ahead and switch PowerPoints here, and we're going to finish out example 3 and 4 on this video, and then we'll stop and we'll do the last 3 examples on the second video. Okay, for example 3, we're going to solve an inequality with a variable on one side. If you'll look at your note sheet, I'm going to read through what it says there. You can add or subtract the same number from both sides of a linear inequality and you will produce an equivalent inequality. So just like with equations, if you add something to one side, as long as you add it to the other, you're good to go. You can multiply or divide both sides of a linear inequality by a positive number, and you will produce an equivalent inequality. You can multiply or divide both sides of a linear inequality by a negative number and reverse the direction of the inequality, and you will produce an equivalent inequality. So when you multiply or divide both sides by a negative, you have to remember to reverse the direction of the inequality. Okay, so let's look at example 3. You have $50 to spend at a county fair. You spend $20 for admission. You want to play a game that costs $1.50. Describe the possible numbers of times you can play the game. Okay, for our solution, first thing we're going to do is write a verbal model and then write an inequality. So the first thing you have to pay is your admission fee, and that's in dollars. So that's going to be $20 plus the cost per game. So that's in dollars per the number of times you play the game, or the dollars per each game that you play. So it's going to cost you $1.5 each time you play the game. And then you multiply that by the number of games. You can use X or you can use G for games. So I'm going to use G. And then that's going to have to be less than or equal to the amount you can spend, however many dollars you've got. So you have $50. So an inequality for this situation is 20 plus 1.5 times G is less than or equal to 50. So our second step is going to be to solve the inequality. We have it. Now we're going to solve and see how many games you can play. All right, so you're going to write your inequality. 20 plus 1.5g is less than or equal to 50. All right, at this point, we're going to subtract 20 from both sides, and so you get 1.5g is less than or equal to 30. And then you're going to divide both sides by 1.5 because g is being multiplied by 1.5, so to undo that, you divide by 1.5. 30 divided by 1.5 is 20, so g is less than or equal to 20. So you can play the game 20 times or fewer. You get plenty of money to do that. All right, let's look at example 4. For example 4, it's not a word problem. You do have a variable on both sides of the inequality statement, so you're going to find that it's similar to solving an equation. And then when we're done, we're going to graph the solution. All right, so we write the original inequality statement. So we have 5x plus 2 is greater than 7x minus 4. Now we want to get the variables on the left-hand side and the plain number terms on the right-hand side. So we're going to subtract 7x from both sides. And that gives us negative 2x plus 2 is greater than negative 4. Now we're going to subtract 2 from both sides. And that's going to give us negative 2x is greater than negative 6. Okay, x is being multiplied by negative 2, so we need to divide both sides by negative 2. When we divide both sides by a negative, we have to reverse the inequality. So that's just something to think about. We're going to divide each side by negative 2 and reverse the direction of the inequality. So we get x less than, because we reverse the inequality, negative 6 divided by negative 2 is 3. So x less than 3. Okay. So the solutions are all real numbers less than 3, and so the graph is shown below. You can see we have an open circle because it is strictly less than 3. And so we have an open circle at 3, and our number line is shaded in to the left because the values to the left of 3 are less than 3. Okay, that's it for examples 3 and 4, and so that's it for this first video. I'll see you again in a minute for the second video for this lesson.